In this video, we shall solve some problems on functional. Our first problem is find the curve for which the functional I yx equal to integral 0 to pi by 4 of y square minus y dash square dx can have extrema. Given that y0 equal to 0, while the right end can vary along the line x equal to pi by 4. Here the line can vary along the curve x equal to pi by 4. Here the right hand end can vary along the line x equal to pi by 4. Here the functional is given by Iyx equal to integral 0 to pi by 4 y square minus y dash square dx. For this functional, the Euler-Lagrange equation becomes y double dash plus y equal to 0. We know that this is a second order differential equation. This is a second order differential equation. Whose characteristic equation is m square plus 1 equal to 0 having root m equal to plus minus I, and hence its solution can be given by y equal to a cos x plus b sin x. This is the solution of the differential equation. Now we are given that the boundary condition y at 0 equal to 0. This is the first boundary condition. If we put this value here, we will become y at 0 equal to a cos 0 plus b sin 0. Therefore 0 equal to a. If we substitute this value, it becomes equation 3 becomes y equal to b sin x because a is 0. The second boundary condition is not fixed. The second boundary condition is given that the right end can vary along the line x equal to pi by 4. From this, we can say that dou f by dou y dash, we shall write this first. The second boundary condition is not fixed. And hence it moves along the line x equal to pi by 4. And this can be this implies that dou f by dou y dash at x equal to pi by 4 is 0. F is our y minus b sin x. Therefore, dou f by dou y dash is nothing but y dash at x equal to pi by 4 equal to 0. But we have y dash equal to b cos x from equation 4. And hence y dash at pi by 4 equal to y dash equal to b into cos pi by 4, and this gives b equal to 0. This gives b equal to 0. This implies that y equal to 0, because a is a 0 and b is also 0. As y equal to 0, we can say that the extremal attains on x-axis only. This implies that the extremal occurs किंवा attain on x-axis. Second example, find the extremal of the functional I yx equal 0 to log of 2 of e raised to minus x y dash square minus e raised to x y square dx. Here the functional is given by Iyx equal to integral 0 to log 2 e raised to minus x y dash square minus e raised to x y square dx. The Euler-Lagrange equation becomes y double dash minus y dash plus e raised to 2x into y equal to 0. This is the second order differential equation whose solution cannot be obtained directly or easily. Therefore, as solution of this differential equation cannot be obtained easily, we convert the original problem into simple problem by substituting x equal to log of u and y equal to v. If we substitute this x equal to log of u and y equal to v, we have when x equal to 0, u equal to 1, and when x equal to log 2, u equal to 2. Thus, for u equal to e raised to x, du by dx equal to also e raised to x, and therefore dx equal to du by e raised to x, which is nothing but du by u. Also, y equal to v, this implies dy by dx equal to dv by dx, which is nothing but dv by du into du by dx. And therefore, dy by dx equal to v dash into u, where v dash equal to dv by du, and hence functional of the equation becomes ivx equal to integration from 1 to 2 v dash square minus v square du. For estimation of this equation 2, the Euler's-Lagrange equation gives v double dash plus v equal to 0. Again, whose auxiliary equation is m square plus 1 and roots are plus minus 1. Therefore, solution of this sequential equation is v equal to a cos u plus b sin u. V equal to a cos u plus b sin u. Putting into original coordinate, v equal to y. Therefore, y equal to a into cos of u is nothing but e raised to x, plus b into sin of e raised to x. This is the solution. Our third problem is example third. If f satisfies Euler-Lagrange equations dou f by dou y minus d by dx of dou f by dou y dash equal to 0, then show that f is a total derivative dg by dx of some function of x and y, and conversely. This is our problem. It is given that f satisfies Euler-Lagrange equation dou f by dou y minus d by dx of dou f by dou y dash equal to 0. We have to prove that, or we claim that f equal to dg by dx, where g is a function of x and y. We can write equation 1 explicitly as dou f by dou y minus dou square f by dou x dou y dash minus dou square f by dou y dash minus dou square f by dou y dash square into y double dash equal to 0. Here we can observe in equation 2 the first three terms on the left hand side contain at the highest first derivative of y dash, the first derivative of y. Therefore, equation 2 is satisfied identically if the coefficient of y double dash vanishes identically. Therefore, dou square f by dou y dash square equal to 0. Integrating with respect to y dash, we get dou f by dou y dash equal to q of xy. Again integrating with respect to y dash, we get f equal to q of xy into y dash plus p of xy. Here pxy and qxy are constant of integration. And may be function of x and y only. Then the function f so determined F. So determine must satisfy Euler-Lagrange equation. From equation 3, we have dou f by dou y equal to y dash into dou q by dou y plus dou p by dou y, and dou f by dou y dash equal to qxy. Therefore, Euler-Lagrange equation becomes y dash into dou q by dou y plus dou p by dou y minus d by dx of qxy equal to 0. This implies that y dash into dou q by dou y plus dou p by dou y minus dou q by dou x minus dou q by dou y into y dash equal to 0. These two terms get cancelled, and hence we can get dou p by dou y equal to dou q by dou x. This equation 4 is the condition that the equation p dx plus q dy equal to 0 is an exact differential equation. dg equal to 0. This implies that dg equal to p dx plus q dy. Therefore, dg by dx equal to p plus qy dash equal to nothing but f. This implies that dg by dx equal to f, which proves necessary part. Conversely, suppose that dg by dx equal to f, and we prove f satisfies Euler-Lagrange equation. Claim is to prove f satisfies Euler-Lagrange equation. We know that f equal to dg by dx from equation 5. This can be written as dou g by dou x plus dou g by dou y into y dash. Thus f becomes dou g by dou x plus dou g by dou y into y dash. Therefore, we can find dou f by dou y. Differentiating this f with respect to y, we get dou square g by dou x dou y plus dou square g by dou y square into y dash. But we have dou f by dou y dash equal to dou g by dou y. Now consider dou f by dou y minus d by dx of dou f by dou y dash. This becomes dou square g by dou x dou y plus dou square g by dou y square into y dash minus d by dx of dou g by dou y. Therefore, dou f by dou y minus d by dx of dou f by dou y dash, this becomes dou square g by dou x dou y plus dou square g by dou y square y dash minus dou square g by dou x dou y minus dou square g by dou y square y dash. From this, dou square g dou x dou y and these terms get cancelled, and these two terms get cancelled, and therefore we will get equal to 0. Thus, dou f by dou y minus d by dx of dou f by dou y dash equal to 0. This proves that the function f equal to dg by dx satisfies Euler-Lagrange equation. Thank you.